How do I get that out of the way? All right. So HMI has there. It's getting all the pictures of all the other people, all the black boxes hidden out of this, blocking my view. Okay. So I just wanted to go over a few things. First of all, happy birthday again to SDO, 11 years and counting. So we started the observation phase right near solar minimum. It was nice of the sun to postpone solar minimum, or postpone cycle 24 until we got launched, because we wanted to get a whole cycle. It was very, very cooperative. We've accomplished a lot, but a lot more needs to be done to accomplish the goals and promise for SDO and for HMI. This would be a brief summary of the current status. Right now, there's been about 2,100 refereed publications using HMI, which is, Dean had a bigger number for SDO as a whole. I thought I just have a scrolling list of this on the screen now, but that's only, 700 milliseconds per per paper, not enough to read the titles. So I'm not going to do that. And I refer you to the ADS and presentations in the next several months to get most of the information about what's been accomplished with HMI, as well as the rest of SDO. Somehow I ought to be able to make that go away. There, okay. So anyway, the original plan, I had talked for 3 minutes about the status, a couple of minutes about calibration, which is still a work in progress, and then talk about helioseismology, goals in progress, and magnetic field work, and then combine the data and look at the future, and then talk about some major progress that comes from collaborative efforts. As it turns out, I've decided to put more of the work, more of the effort here on the status questions and the issues that we have, and a little bit of discussion of some of the really nice science work that I'm more familiar with than the other 2,100 papers. So first, HMI is doing well itself. It's not perfect, it's maturing well. We are having the expected transmission loss through the front window. So it's down about 3% per year, and that's about what we expected. This is the plot of the average values from each camera. We have two cameras, one on the side, one on the front. The one on the front is dedicated to the line of sight observations in the 45-second cadence. And the one on the side is dedicated to the vector fields. And since the last 4 years, we've merged the two together. So we do the vector fields with both cameras. So we get a 90-second cadence instead of a 135-second cadence. The filters, there's 3 tunable filter sections to get to our narrow passband. And they drift with time. And that was known, it was expected. It worked that way with MDI, it worked that way with Gong. So the Michelson interferometers tend to drift in their center passband with time. We're not sure what it is. We think it's just the changing of the glue between the layers changes the spacing of the Michelson just by a tiny bit. So this is the changes over the years, and it looks like small numbers. Like the narrowband Michelson has drifted 11 milliangstroms, which is like a sixth of the width of the final transmission profile. But there's 49 meters per second per milliangstrom. So that means we have to retune it, and we can retune it anywhere we want. So we retune it about once a year as these drift. So also we have very good coverage. The data coverage is really good. We wanted in the order of 98% coverage for the helioseismology. And this is a typical plot of one of the worst times. This is during an eclipse. The eclipse season, when the spacecraft passes behind the Earth for a couple of hours a day for about 2-3 weeks, we have no coverage during that time, but the rest of the time we do. And this plot shows blue when we don't have any images, when there's nothing in the way. The amber here is when the eclipse, when the Earth is in the way. And the ones that are green just means that we don't have, for any given product. And remember, we take filtergrams, a sequence of 12 filtergrams for the vector, for the line of sight, and 24 filtergrams for the vector. It takes all of those filtergrams to make the product, but by averaging, interpolating between them, we can take them at a nice cadence. We can still make all the products. So the green marks are when there was, one filtergram out of the set that had to be interpolated over because of particle hits or because we did calibrations. That's what the vertical lines are. Is every day at the same time at noon and midnight, we SDO noon and SDO midnight, we do some calibrations. Now the Science Center, the JSOC, the Joint Science Operations Science Data Processing at Stanford is part of the HMI project. So it's not just running the instrument and taking data and doing analysis, it's also managing the data flow for most of the data from SDO. There's a good sized chunk that goes to Colorado for the EVE instrument, but most of it comes to Stanford, and then from Stanford it goes to obviously Lockheed and to NASA and to NOAA and to Air Force and others who need it for space weather predictions. And then a few days later, it's available to everybody in this sort of what we call final form. And you'll see in a little while that we hope it isn't quite the final, but we'll fix that. So the JSOC plays a key role in dealing with the numbers of files that we have. I count more than 1 billion files between AIA and HMI. We have about 407 million level 0 images, and then the same number of level 1 images. And then we have higher level products for HMI that brings the total up to a fairly good sized number. And we have 15 or 16 remote data sites, remote data centers, where they have access to the full database and get the current data as it's produced, the final data as it's produced a few days after the shutter was open for each one. And then beyond that, we have most people. We have about 3.5 million individual export requests, averaging about 900 a day. It started out slower. Now it's very often 1,500 a day. So we're beginning to send data to the Goddard archive. Not all of it, just some of the raw level 0 data at first. And then later the level 1 data and the level 1.5 and above for HMI. And combined, that works out to be about a petabyte per year. And we'll omit the telemetry data because that's a pain to unpack to level 0. And level 0 contains the images that were there at the camera on board. And so we leave out the part where it was compressed and sent down and to us and then uncompressed. We also now have recently improved the metadata formats for the FITS files that we make. So now they're standard compliant. There's some little details in there that kind of got in the way. Like we thought that a NaN should be a perfect value for a missing value, but FITS doesn't allow that. It requires it in floating point image data, but not in the headers. So anyway, we fixed that stuff. But once it goes to an archive where it's FITS standalone files, some important capability is lost unless the archive has some really good search capabilities, because it's going to have to pick which you want out of a few billion files, and some subsetting because the files are big and these time sequences are big. So if there's not a way for people to extract just the part they want and not the whole thing, the productivity is less. So I mentioned that calibration is still a work in progress. And we expected that when you design an instrument, you can design it so that the statistical uncertainty isn't a problem. You have enough light, you have enough jitter taken into account, you have ways of dealing with the statistical errors. But the systematic errors always dominate, and they validate Murphy's laws. But what we didn't expect was the leakage of the orbit velocity into all of the calibrated quantities. It's only about a 1% leak, so that the Dopplerograms have about a 1% of the measured velocity that varies during the day. And that's, we thought we'd manage that in the design. And I think if we knew at a better level than we thought what the filter profiles are, we would take care of some of this. But there's also temperature changes during the day. So SDO is on the sun side of the Earth for half the day and behind the Earth for half the day. And the Earth is a warm source that actually changes the temperature of our front window. So that actually causes some problems. So we're beginning to work on that. And I wanted to show a little bit of the scope of that. So the blue lines on here are the orbit velocity, the 3 kilometer per second orbit. And then the upper left is the mean velocity. This is for, of course, I can't see the label, which day it was. It doesn't matter because it's blocked out by the Zoom screen at the top. But the orange one here is the mean of the Dopplergram, and I fit solar rotation to it, and this is the A coefficient, the equatorial rotation rate. This would say that the sun's rotation changes at plus or minus 60 meters per second, every day. We know it doesn't do that. So that needs to be calibrated out. And this is the differential rotation, and this is a spurious apparent north-south motion. And we know that comes from the filters, that there's a variation across the field of view of the 0 points. And notice that it has a different effect in the side when we're on the day side, which is these peaks, and the night side is different. So there's something different in the night side that makes it so it's not just a simple leakage of the velocity, but it's also probably thermal is the source of that. So that's the source of the 12-hour that also shows up. And if you look at umbras, you see the same thing. And if you look at the power spectrum of that, you see the 24-hour and 12-hour peaks. So it's there in both the line of sight camera, and it's there in the vector camera. And they, of course, are different because of the way the processing is done and the calibration is done. This is what you take 7 days and take the average of that, leave off the places where there's strong field, and then remove the orbit as best you can. And this is a map of what's left over. And this is just the power at exactly 24 hours. You see that it's not uniform across the disk that it's changing. It's more in some areas near the limb and in a couple of areas. You might say that it's the magnetic field is somehow causing that. It appears to be in the same place, but it's not. This pattern is there all the time. There's just some samples. The pattern is still the same, but the magnetic fields are different. So it's not the magnetic field. Now, some of the ways to fix that are to just measure it in the end product and fit with the rotation and with the orbit velocity. and then remove that from the end product. That's one of the ways of dealing with it, and that's what Yang Lu does and what some others do for the vector field. And the other way to do it is to fix it at the beginning, fix it at the instrument side, and that's what we're working on. We've just started a project involving also Goddard and NSO to try to, in the next year or so, try to really make a good improvement to it. There's another systematic problem that turns out that SOLAS on the ground has for vector fields, and that is that the transverse field is higher signal to noise and less sensitivity in trying to measure it. And the line of sight field is stronger, so the line of sight dominates in weaker field regions. And so any small systematic difference in the instrument will show as the field's apparently changing direction of the transverse component as it crosses the disk. And SOLAS has the same problem, but with the opposite sign. So that is really interesting. It's a clue. There's work going on to resolve that also. Now, most of the studies that are done are not seriously impacted by the calibration issues. Like seismology is really, it's only like a third order effect if it's there at all. So it's, but it does affect following active region evolution as it crosses the disk. If there's a 5% change in the flux, that's due to the instrument and not due to the sun. So one of the, so the global seismology is continuing, and there's a lot of work going on now. The traditional seismology from the late 70s, early 80s is still happening. And several years ago, I think it's now 4 years ago or 5 years ago, Mike Thompson gathered a group of most of the helioseismologists, the global ones, to try to develop a solar rotation consensus and improvements to the inversion methods, improvements to the peak fitting. And Jan Christensen Dalsgaard has now taken over, the unfortunate loss of Mike Thompson. Put a dent in the effort, but this is picking up, and there's monthly meetings now, and there's 47 people on the mailing list. So it's proceeding, and stay tuned for better defined results of the rotation, global rotation. Anyway, efforts continue. There's plots like these that show the zonal flows and the way the zonal flows are intertwined with the magnetic fields. And that's known as sometimes as the torsional oscillation. And it shows that cycle 24 was different from cycle 23, and the cycle 25 is already was visible quite a while ago. And in the toroidal field, which we do from WSO measurements, that's why I didn't show it here. It's also visible long before minimum. So, and Dean mentioned Rossby waves. This is some work from a group at Max Planck, and they used the ring diagram method that is one of our standard products. Maps, helioseismic maps at various resolutions at a high cadence. High cadence meaning days, or pieces of a day. The solid line is the theory of what the Rossby wave would do in azimuthal order and frequency. And the little dots, the darkenings here are the observations. So it really is very convincing that these are Rossby waves. One of the other areas that is actively being worked is the deep meridional flows. And it's been measured by several groups using HMI and MDI and GONG data. And they detect wave travel times over half of the convection zone or deeper, with a few hundred milliseconds, a few tenths of a second difference in travel time, averaged over many hours. And the systematic errors that are larger than that need to be removed, the center to limb effect. And there's different ways of doing that, and different ways of trying to turn the time distance phase changes into flows. Recent work at Max Planck comes up with a different answer, that there's only one cell and not two. But I think that it's still an open question, and the background is removed differently in the two different methods. So we'll have to see how that works out. The far side fields, far side detection of flux on the surface is also still continuing. The original method that started around 2000 with the early HMI data and is continuing. So that was MDI data. That was the time of the beginning of the discussion of the living with a star, and it was presented at the solar physics division meeting in a drill and roof in 2000. But that method is still going, and you can see the data on the JSOC, there's links on the left-hand side of the homepage to find that data. There's a new method that Junwei Zhao has developed along with Rui Zhu, and it's using time distance method instead of the holography, and using many skips from the front to the back and back to the front again, and it gives cleaner results. And these new far-side images will be available in production soon. And also there's calibrated images that is being worked on. This is a plot showing the difference between the old way and the new way. And you can see, you have a little more time to look at this. I assume that these presentations are all available somewhere online when we're done, so you can go back and look at them. But you can see regions that are just moving from the front side to the back side that show up more visibly in the new method than in the old method. And there's been a project to, well, that's interesting, there it goes, to calibrate it better by using machine learning and 304 data from stereo and AIA. So, sorry about that background. There's some final construction on our new room where I'm sitting now. in our and they were supposed to be done yesterday, but apparently there's still some work this morning. I don't know what they're doing up there, but this is the Dopplergram. You do time distance, and you get a far side map showing where flux is, but not anywhere well calibrated. You can also take the 304 data from AIA and use machine learning to have it generate a magnetogram or a flux map. And that works very well. When you look at the flux map generated, it's very much like the measured one. So you can train machine learning from 304 to flux. You can do the same with, use that same training using stereo and get a flux map. Then you can compare that to the actual flux map and learn how to convert the actual one into a flux. So, and that's being developed and it's ready, almost ready for prime time. So that'll help with models of the heliospheric field. and solar wind. The line of sight magnetograms are also continuing, as well as the vector fields. And there's products there that, so these synoptic charts are made every day and available online. But some of the products are computed when requested, like the polar field plot, which Monica Bobra put into the Jupyter notebook. So it's. We have to do it before the inspector gets yeah. Okay, one more cut up there, I guess. Another product is made is QMaps, which are showing the topology of the coronal field derived from the photospheric magnetic field. So this one shows footpoints of open flux. This shows the separatrix between flux that are fields that come from one region or another. And as you go up in altitude, it simplifies. And so then this is getting to be like the current sheet. But you can see where it comes from. And it's a very interesting way to do it. That is also available. And I'm not sure this is going to work. I think it's much too fast and you probably don't see it. But there's a movie there of basically many years. So the vector fields combined with AIA for verification are really interesting. You can this has just been accomplished and is leading a way for the future. There's a project that just finished called CGEM, a coronal global evolutionary model that starts with vector fields and shows what you can really do with a collaborative group of different skills. So it was Berkeley, Stanford, and Lockheed, and then 5 other institutions also joined as part of it. And they end up with a model that can start with the fields on the sun and compute what you would see in the corona, what you would observe with, say, AIA. And this is what they do. They start with the sun and get a time series of vector field, get a time series of line of sight velocity, use the vector field to get the horizontal velocity, and then combine all those and get a time series of electric fields, maps of electric fields. Then that data can then be used to model the coronal situations. Then you can use that in MHD models as input MHD models to either look at an active region or to look at the whole heliosphere. And that is now products that can be used. Some of us at the CCMC and some of us run at JSOC. This is an example. This is, the input is the magnetic fields, and this is the simulated synthetic emission above that region, and that's AIA at the same time. So it picks up the essence of what's there, and is a good place to begin other works. So where do we go from here? And there's new opportunities to benefit from now with the 25 years of full disk Doppler and magnetic field data. And there's also interpretation issues to still solve. For helioseismology, we don't know how to make robust inferences where there's strong fields. To do the inversions, you have to have a knowledge of the atmosphere to go from the travel times or to phase changes in waves. You have to know what the atmosphere is. And that requires the knowledge of the subphotospheric field, which requires knowledge of the atmosphere to do the seismology. So there's some work that needs to be done there to do that. There's progress, but it's still, you can't really have deep flows that under active regions that you have really high confidence in yet. And as I mentioned already, the deep flows to do this, the meridional flows, for instance. You need to understand the center limb phase shifts, and there's still differences there in understanding. The progress with the simulations and with more physics is happening for both seismology and the fields. So it's what I call the land above. There's two halves of the sun. The sun, there's a part you see in the sky, and there's beneath that, the interior, and there's a land above, which is where many people are spending their efforts. But and so CGEM is talking about the above, the atmosphere. But I think it's nicely summarized with these the final statements in the final statements in the paper that was just published for the final results of CGEM. And so the questions are, are the observed evolution and resulting estimate of energy accumulation sufficient to account for the release of CMEs? And if so, we're on our way to really physics-based modeling for really space weather. But if not, then there's still other work to do. So it's a turning point. And we're in a world now of still increasing computational capabilities, access to data. AI, machine learning is really making some progress in some areas. And there's new data coming from complementary perspectives, such as Solar Orbiter and Parker Probe and DKIST. We now have 22 years of continuous, we have a whole 22-year cycle of helioseismic and magnetic fields and coronal structure. And so now I think we don't have a robust understanding of the source of solar cycles, and that's in the interior. So now is the time to really combine the data, the models, the simulations, and different groups of people to try to get a good handle on the interior. It's time to put it all together. It's time for a COFFEES. And COFFEES is one of the drive, NASA heliophysics drive data science centers that is in a phase 1 study. And it's really showing that, yes, you can actually combine these and begin to make real progress. So that, the real progress comes from collaborative efforts, where you have people with different skills, different backgrounds, and different approaches to the analysis, to the data, and to the models. And in the first years of helioseismology back in the 80s, it was really exciting. Both theory and observations built upon the other, and each pushed the other. So you had seismology that said that the interior of the sun was certain structure, and then the models say no, that wasn't right. Well, actually, the convection zone is actually deeper than the models say they should be. And then you continue and back and forth like that, and then the rotation turned out not to be on cylinders, like all the models said it must be. So as you add more physics and more understanding, it gets better. So we're now seeing a similar symbiotic collaboration between more realistic simulations of most regions of the sun and observations. So it's going to be fun, I think. And in cycle 25, we'll have not just SDO, but we'll have Solar Orbiter, Parker Probe, and DKIST. It's going to be fun. And one of the goals has been of SDO that I think Barbara didn't mention, Dean didn't mention, but it's the driving goal. It's to my mind, that is to learn if solar activity can be forecast, and if so, to learn how to do it, so that future missions for future cycles could have the tools to make the forecast in scales from hours to decades. But if what we're learning from 23 and 24, and we'll learn in 25, to be applied to cycle 26, we need to get started now. It takes a solar cycle to go from a concept to an operational spacecraft, operational capability. So I think we have to encourage the development of future missions. For some of these things, you just can't do from the ground. It may be that it's China or Brazil that provides the data, but and then maybe the interactions with China and science will get better when they have the data and we don't. Okay, anyway, that's I think what I had to say.
All right. Thanks, Phil. Let's see if I can clap for you. If people want to clap or maybe send there, I'll send you a party favor.
Okay.
Very, very nice talk, Phil.